For decades, science fiction has sold us a very specific vision of lunar living: gleaming glass domes and bright white habitat modules sitting proudly on the dusky surface. The thermal reality of that environment is entirely unmanageable. The lunar surface experiences temperature swings of 500 degrees, shifting wildly from boiling heat in direct sunlight to deep freezing cold the moment night falls. Then there is the historical violence written directly into the terrain. Because the moon lacks a protective atmosphere, it is subjected to a constant bombardment of micrometeorites traveling at tens of thousands of miles per hour. Even if a structure survives the impacts and the heat, the surface offers zero protection against unfiltered solar radiation, which actively degrades human cellular structure over time. To block that radiation, you would need meters of lead. Launching enough shielding for a single habitat would require more payload capacity than our entire global rocket fleet currently possesses. This is why the engineers at NASA headquarters have recognized a harsh truth. Building a sustainable presence means abandoning the exposed surface entirely and moving inside the crust. The sunlit terrain is an environmental death trap. To survive, we have to structurally bypass it altogether. Billions of years ago, ancient subterranean rivers of liquid magma tore through the lunar crust. When they drained away, they left behind massive, hollowed-out geological veins known as lunar lava tubes. The thick layer of basaltic rock that makes up the ceiling of these tubes provides natural, heavy-duty environmental armor. It blocks out the deadly solar radiation and completely neutralizes the threat of micrometeorite impacts. To understand the physical scale of these voids, look at this aerial view of a dense metropolitan scape city. The largest of these lunar tunnels are wide enough to house human infrastructure of this exact magnitude. These ancient geological relics provide the exact structural foundation we need, giving us billions of dollars worth of heavy shielding entirely for free. But turning a raw, pitch-black, unpressurized cavern into a livable environment requires a massive feat of civil engineering. Phase 1 deploys massive structural bulkheads, sealing cavern segments for a pressurized atmosphere. But a hidden hazard remains: microscopic lunar regolith coating the walls. Phase 2 neutralizes this razor-sharp dust by applying a sealing layer and activating advanced air filtration. Once the air is safe to breathe, the city has to sustain itself. Keeping a city of thousands supplied with air and water from Earth requires a non-stop cargo train of heavy-lift rockets. The fuel costs alone would end the mission before the first year is out. Phase 3 focuses on the cold traps created by these caves. Because the sun has not reached these interiors for billions of years, any water molecules that migrated into the tubes remain frozen in the dust. This ancient ice provides the raw materials for drinking water and, when split, the oxygen and hydrogen needed for breathing and fuel. Surviving inside the tubes requires a delicate engineering equilibrium, completely sealing out the abrasive dust while aggressively extracting the life-saving ice. When those phases are complete, the resulting architecture is a thriving, multi-tiered metropolis built seamlessly into the dormant rock, lit artificially from within. This approach marks a shift in how we handle off-world colonization. We can no longer afford to force fragile, Earth-like structures onto hostile environments. Instead, our survival strategy relies entirely on adapting extreme alien geology to serve as our primary physical armor. Mastering this subterranean blueprint is the hurdle we must clear before we can consider moving further into the solar system. Because when we look at this rocky, orange-tinted Martian landscape, we are looking at the exact same lethal radiation threats we face on the moon. Mars will require the very same subterranean adaptation. The engineering math adds up, but living out your life in a sealed, pitch-black void requires extreme psychological endurance. The real question is, would you have the psychological fortitude to abandon the sunlit surface and become a subterranean citizen 240,000 miles from home?